All right, let's look at question 4. It says, let f be the vector field minus yi plus xj all over x squared plus y squared. Our job is to show that the line integral of this vector field f over any simple closed curve C that encloses the origin and is given a counterclockwise orientation is equal to 2 pi. Okay, so here is a simple closed curve C that encloses the origin right here. It's given a counterclockwise orientation. And so our job is to show that the line integral of our vector field f here over this blue path is equal to 2 pi. And I make a note here that since our vector field is not defined at the origin because of the division by 0 that would result at the origin, Green's theorem does not apply directly. Okay, Green's theorem required that our component functions p and q possess continuous partial derivatives on the region enclosed by our curve C, but we're not even defined at the origin here. Okay, so Green's theorem does not apply. So what we're going to do is modify things a little bit so we can tie in some ideas from the last video on what we referred to as the modified form of Green's theorem. All right, so the first thing we're going to do is introduce this little yellow circle here that I'll call C sub A, where A is the radius of the circle and the circle is centered at the origin. And let's choose the radius to be small enough to ensure that this circle C sub A is completely contained in the region D that's enclosed by our curve C. Okay, so now what we'll do is consider this region that I've shaded in white between the yellow circle and the blue curve C here, and I'm going to refer to that region as D prime. Okay, so notice D prime does not contain the origin, and so now the components of the vector field f are nicely behaved on D prime. They will possess continuous partial derivatives on that region. Okay, so what I can do is apply this modified form of Green's theorem on D prime. Okay, and now D prime not being simply connected means that we do have to be careful when it comes to the orientation of its boundary. Okay, and as we discussed in the last video, for D prime's boundary, when I'm on this outer boundary portion in blue, so in other words, as I move along the curve C, okay, I'm going to be oriented counterclockwise. Okay, so my region D prime is off to my left as I move along the blue path. But for the yellow circle C sub A, okay, now I'm going to have to move clockwise. And the reason why is I want the region D prime to be off to my left as I move along this yellow path. And that will be the case if I move clockwise. All right, so now let's go ahead and look at the integrand of the double integral in this modified form of Green's theorem. Okay, so if I go ahead and compute the derivatives of partial q partial x and partial p partial y and subtract, okay, I'll find that that is exactly 0 on this region D prime. And that's a pretty straightforward calculation. It's actually part of question number 2 on your quiz this week, so I'm going to leave that part to you. But what this implies is that the double integral then on the right is equal to 0, which is quite nice. Okay, now for the line integral on the left, I'm going to break this up as the line integral over the blue boundary piece plus the line integral over the yellow boundary piece. Okay, so I have my blue piece here, and then I have my yellow piece here. But keep in mind, right, that I'm orienting the yellow piece in a clockwise fashion. Okay, so if I write the integral symbol over C sub A, if I use that notation to denote the counterclockwise line integral over this circle, then if I integrate clockwise like I'm doing here, then I have to put a minus in front of that to account for the reversal in orientation. So now I have that the difference in these line integrals is equal to 0. So that implies that this integral over the blue path C is equal to, now this is the counterclockwise oriented line integral over our circle C sub A of our vector field F. And you computed that in question number 5 on last week's quiz. Okay, And that's just the circulation of our vector field F over that circle C sub A, and you found there that that was equal to 2 pi. And that completes the proof. All right, so that's going to do it for this video. I will see you in the next problem.